Good morning to everyone. I'm very happy to see you back in my class. So I almost know everyone in this class. Yesterday we had the introduction of the unit. So if you missed yesterday class, the session has been recorded. You can always watch the recorded lectures or tutorials on Collaborate Ultra. And for today, we keep completing the review for vector operation. So vector operations are very fundamental for this unit. And the reason is the quantities that we want to measure, the most important ones are the forces. So you want to know the forces in a structure such that you can get an idea about the performance. If we know the forces, we can decide about the material, about the geometry, about modifying the structure. So that's very crucial to understand the forces. And unfortunately, forces, the nature of forces are vectors. They are not scalars. And to understand the forces, you need to know how do they add together, and sometimes you have to multiply the vectors and all that. So we start with the very simple vector analysis that is two-dimensional. But what we say is easily applicable to the three-dimensional. So we start with the 2D, and then once you are comfortable with that, we move toward the three-dimensional. So one thing you want to know is the technique we studied yesterday, that was method of triangle or trapezoid, okay, parallelogram. And that doesn't work always. If you have multiple forces, a triangle is not convenient, parallelogram is not convenient. So what we do in this instance is, no matter how many forces, we break each individual force into the X, Y, Z components, and then it's easy to combine them. Why? Because all X components can be added like numbers, like scalars. All the Y components can be added like numbers. All Z components can be, because they are collinear. And then the problem reduces to have one big X component, one big Y component, one big Z component. This is, you pretend you are dealing with one single three-dimensional or two-dimensional vector, which you have their components. The components being big Fx, big Fy. So what are these? These are the scalar summation of the magnitude for those components. So don't worry, we give you some practice to be comfortable with that one. But for now, that is the outcome. That is the outcome. You have all X components added together, represented them by, this is a Greek letter sigma. Sigma represents summation. That is the summation of all X components, summation of all Y component. And then your triangle is a simple triangle. This is a right triangle. Aisha, come in. So with the right triangle, you don't have to worry about the sine law, cos law. This is all about the Pythagoras theorem. So X components squared plus Y components squared is equal to the hypotenuse squared. So that is what you get. But before getting to that, you have to do some homework. Okay, now please listen carefully. I'm just refreshing your understanding about the unit vector. So here I'm going to use a analogy. What is unit vector? Imagine a unit vector as a parent. So this is a unit vector. So what is the attribute of a parent? A parent has some properties, but most importantly, the parent is not very tall. The parent is only 1 meter. Okay, the child, they are very similar to the parent, but they could be taller, they could be shorter. So what do I mean by that? If that vector, I call this unit vector or parent unit vector. So this has a direction. Of course, the direction is theta. And it has a magnitude. The magnitude is 1. But all the children, they are similarity to their parent. The similarity is that angle. they keep that angle. But apart from that, the child could be taller, they could be smaller. If the child is taller, that unit vector is multiplied by something larger than 1. If that is shorter, the unit vector is multiplied by something smaller than 1. And at the same time, the child could be male, female. So that is when you have the change of direction. So still, something like this one is a child. Even though the parent is that way, this is the other way. So why this is important? Because when we want to study the vectors, it is most convenient to study the unit vector, and from unit vector you generalize things to the vector itself. And then one important thing is that later on we have to deal with position vector and the force vector. Force vector, position vector are along each other, but they share the same parent, right? So once you know the unit vector of the position vector, you know the position vector of the force. So that's a trick. This is the cheating. We cheat. You want to describe the force, but you only have the position vector on which the force is established. So what you do is you find the unit vector of the position, and that is the same as unit vector of the force. So I hope I haven't made you confused, but maybe some examples make this more clear. Here we have two scenarios. Either you are provided with the components, and from the components you want to get to the resultant, or you are given the resultant, you want to break it into the components. So two-way, depending what inputs you have, what outputs you have, we do Ainigel come in. So yes, and then this is an example where you have three forces. So three forces, we cannot add them using triangle. Triangle is most suitable for two forces. Even when this becomes three-dimensional, even two vectors in a triangle is not easy to solve because the angles become spacious, right? So yes, the Cartesian components are very convenient. No matter how complex the problem is, how many forces, whether this is three-dimensional, you can use that technique to add or subtract the vectors together. All right, so one question here, why in this diagram I'm showing the vectors with dotted line and the components is solid line? So that reminds us, look, you don't have to count something twice, right? People say you can't have a cake and have it. If you eat the cake, you ate it. There's no cake anymore. So once you break that force into two components, this is a ghost. This doesn't exist anymore, right? So when it comes to adding the forces, I'm using the dotted line to remind you, look, that you shouldn't count it twice. You already broke it into the component. Only count the components. Forget about the vector itself. Okay, so that is just a reference. This is a reference to remind you that these two are being generated from that vector over there. And now the problem is easy. All you have to do is f1x, f2x, f3x, add them together like numbers. f1y, f2y, f3y, add them like numbers, and then you have one big x, one big y, and one right triangle. Just solve the Pythagoras theorem, and that give you the resultant, give you the direction for the resultant. So this is, yes, when you are adding, you have to consider the direction. Maybe one component x is in positive, one component of x is negative. So what you do is you subtract the second one from the first one. So that's like a arithmetic summation. And then, yes, like I said, depending what are the input, what are the outputs, sometimes you have the component, you want to find the resultant. So that is to add x component, y component, and dividing total y divided by total r, tan inverse to get the direction for the resultant. And sometimes you will be provided with the resultant and its magnitude direction, and you want to resolve that into component. So that is using the simple trigonometric equation, which is cos the angle is adjacent divided by hypotenuse. and sine of an angle is opposite divided by hypotenuse, right? So these two equations, we will be using them very frequently. I don't know in high school how you just help yourself to memorize this one, but that is something we use very frequently, and make sure you can use them confidently and robustly. Okay, first example. All right, with the first example, we have two forces. And yes, of course, we can add them using the triangle, but here we want to practice the method of components. And method of components, I mentioned that these are the two equations you use, cos and sine relationship, but there is even something easier. In some examples, instead of giving you the theta, they give you a small triangle here. That small triangle, how do you use it? We use the similarity of the triangle. So the big triangle is similar to the small triangle. So here I can easily say f2x divided by 12 is equal to f2y divided by 5, right? So or even if I know the magnitude of f2 and I want to find is fx, right? So how do I find f2x? F2x is simply, that is the magnitude of this one multiplied by cos this angle. So this angle and that angle are equal. So cos that angle is 12 over 13. So that is multiplied by 12 over 13. That is 1. This is 2, 20. Right? Yeah. One more time. Yes. Yes. So that is f2x. And this is theta. So f2x is what? f2x is the magnitude of f2 multiplied by cos theta, right? Correct? And this theta is equal to that theta. Why? Because there are two parallel lines with one line. So this angle and that angle are equal. So therefore, this is also theta. And in that little triangle, how do you define cos theta? Cos theta is adjacent divided by hypotenuse, which is 12 divided by 13. All right. So that is, you have to be comfortable with both ways. In some problem, you will be given the angle. In some problem, you will be given the little triangle. In some problem, you will be given something else. You have to innovate and just invent your formula. Is that clear? Can we move on? Questions? All right. So that is, first we start with F1. How do I break the F1? F1, I know that the y component is, yeah, just in every problem, you have to apply the formula yourself. I mean, that I could have given you 60 degrees instead of 30. And in that case, that was, the x component was 200 times cos 60. But now that I give you 30, you want to find the x component. This is the x component. That is the sine of 30. Sine of 30 is equal to the cos of 60. All right. So this I hope you still remember from high school, not long ago. And that is when you break the first force into two components, and then you have them. Then you break the second force into two components, you have them, and so eventually you add x components together, y components together, and combine the big triangle using the Pythagoras theorem. All right, so eventually that's what you get. Here, that is the resultant force. The resultant force is being shown by a red triangle, and that red triangle has a big X, big Y. The big X is 140, the big Y is 173, and the angle between them is 27 degrees. All right, so that is called the method of, this is for coplanar forces, Cartesian coordinate. If you had the three-dimensional, they were not coplanar, still you could have done the same way. The difference was you needed to have the angle in the three-dimensional, so that's a little bit more involved. I get into that soon, but then you have still a big right triangle to solve with the three fx, fy, fz resultant. All right, so if you want to try this problem yourself, I give you a few minutes, 2-3 minutes, and you try, and then we try it together. Okay, so 5 minutes from now. Okay, so this is a type 2 where you are provided the angle, not the similar triangles. So the only thing is when you are breaking this component, you are looking to that triangle. So alternatively, if I had this angle, I needed to solve the second triangle. So with this triangle, uh, x component is cos 45. Sorry, x component is sine 45, and the y component is cos 45. But the x has a negative sign because that's in the negative x. For F1, both components are positive. X and y are positive. So here we have the solution in your slide in case if you want to check that. So let's go to page 44 and try the second problem. Okay, so this is, like I mentioned, most of the material has been, the worksheet has been digital. You don't need to buy the textbook. So 45, the second problem. All right, let's try that together. It is too small. Can you see it over there? Or just let me make it a bit small, large. Okay, resultant force. Let's call this, I mean, labeling is very important in every problem. If you do the labeling properly, the solution become easier, right? So I call this F1, F2. And that one, I call this the x-axis. And it is up to me. I mean, I can get the y-axis in the downward direction or upward. So conventionally, this is up. So in this case, F1x, that is the magnitude 200. And is this cos 30 or sine 30? X cos. Thank you, Shah. And of course, if this is cos, Fy1, that would be 200 sine 30, right? And then is this positive or negative? F1y. Negative, yes, because according to that y direction, that would be negative. And what happens to F2? F2x, F2y. So F2x is the magnitude 500. And what angle should I account for? 30 plus 40, which is 70. And is this cos or sine? Cos, yes, cos 70. And is this positive or negative? Well, x is positive, and that is negative, right? Okay. So this unit, there are relatively some good amount of material put together. I assure you that if you attend the classes, you definitely would have a very good score in this unit. All right, but it might be just, you might get scared, but all you have to do is just come to the classes. This term I have increased the weighting for the lab practices. So that means you don't have to worry too much about the mid-semester exam, final exam. I reduced their weighting to 25%. And even those 20% you should easily get. But in case if something happened during the exam, you just panic or whatever, there are plenty of other scores you can secure without the exam. So don't miss the tutorial classes, don't miss the lectures. That's all I'm asking. I assure you, you will be in getting a good score from this unit, very good score. All right, and then you do what next? The next is adding this number together to have one big X and one big Y. That is just you add the numbers, and eventually you have the resultant from the Pythagoras theorem. That is the big X squared plus big Y squared, and then the big theta is tan inverse of big Y divided by big X. Any question? This is just from a triangle, from the trigonometry. We know in a triangle. This is the, sorry. These are in the slides. Yes, these are, I mean, summary from the higher school. I believe you've been told this in a different ways. But if you wonder where this is coming from, this is theta, and this is sigma Fy, this is sigma Fx, and this is R, right? So in this triangle, theta is tan inverse of opposite to the adjacent. And R is Pythagoras theorem. That one is squared plus this one is squared, root is equal to that one. So let's go to page 55. Okay, page 55. You tell me whether you want something simple, medium, difficult, and then how about 2-7 or 2-8? Which one? Simple. Okay, I like that. Let's do simple first. That's very reasonable. Yes, I digitized this question from the textbook. In case if you don't want to buy the textbook, this is all you need. That is only Canvas. Canvas, each week there is a link where you find all these worksheets, yes. Okay, so in this case, that's a combination of the angles and the similar triangles. So how do we do that? It's simple. You don't have to worry about the labeling. The forces are already being named. They have a name, F2, F3, F1. So, and here I'm going to do this a little bit different. So, for example, F1, I want to write this in a Cartesian coordinate way. So that is a 0I plus 300J. So everyone can see where this is coming from, okay? And if I want to do the same fashion for F2, how can I write this? F2, that is the X component, which is 450 times cos 45. And because this is in a negative X direction, I put a negative at the back. And then its unit vector is I. plus, what is the y component? The y component is 450 sine 45. And then finally, the unit vector of that is j. So can you see that? And what about F3? F3 is 600. And then this is the cos the angle. Cos of that angle is 3/5, isn't it? Plus the magnitude of F3, which is 600, multiplied by sine of this little angle. Sine is opposite divided by the hypotenuse, which is 4/5. And now what you do with that? This is simply you add all I components together. That give you F3, yes, of course. F3. F3 is F3xi plus F3yj, correct? So what is F3x? F3x is 600 multiplied by cos of this angle. This angle, whatever that is equal to that angle over here. And with this little triangle, how do you find that angle? That is, cos of this angle is adjacent divided by the hypotenuse, 3/5. And the second one is 600 multiplied by sine of theta. Sine of theta in this little triangle, that is opposite divided by hypotenuse, 4/5.
For all of us, like for F1, F2, and F3, the exercise is same. That would be like 90 plus something.
XY are the same, but each force has its own orientation. This one has a different angle, the other one is vertical, the other one is in the second half, right? So each force has its own magnitude, its own direction. So you treat them privately. So these are a big Fx, a big Fi, and then eventually the resultant would be root of net x value squared plus net y value squared.
I think that first is not waiting on the
F3?
Yeah,
F3 doesn't have any x component.
Sir, can you do it in a long way?
You want me to write in a long way? Yeah, sure. So if I want to write F3 in the long way, that is the magnitude of F3 is 600 multiplied by cos of theta. Cos theta I plus 600 sine theta j. And that is equal to 600. Cos theta is 3/5. And the next component, sine theta. Sine theta is 4/5. And then this can easily be simplified. That is divided by 5. That is like you're divided this by 10. This is 60 by 6i plus all right. You have to speak up. Oops, yep, sorry for that. Let me zoom out so you can see everything together. Huh? By the way, these are all recorded. You can access them on Collaborate Ultra. All right. Everyone is in the same page. Just please stop me if you want me to. Okay, so that was the simple one. Let's go to something medium. All right. So what about F210? F210. All right. So in this case, the problem labels are not there. So I suggest we start with labeling the forces. That makes make the solution much easier. And here, okay, we have been told about the resultant. We've been told that the resultant, I call this R, that is horizontal. It doesn't have any vertical component, all right? It means that is only with an I component plus 0 J components. That's one thing. And also we know that these two forces together with F, they will be resulting in R. So let me call this one F1. I call this F2. And here we should have R is equal to F1 plus F2 plus R plus F, sorry. Hello. All right, so where do I start? Let's just start with F1. Who can help me with writing F1? That is the magnitude multiplied by cos of that angle in this little triangle. So what is that cos? Cos is the adjacent divided by the hypotenuse, which is 5 divided by 13, right? So here, let me zoom in. This is 3 or 5?
In the force, the black one is 325. It's not 300.
Oh, 325. Yeah, thank you for that. And cos of this little angle is adjacent divided by hypotenuse. This is divided by 13. And that multiplied by I, correct? And then the y component is plus the magnitude 325 multiplied by sine of this angle is opposite divided by hypotenuse. That is 12 by 13. And that is J. All right, so the next thing is, how do I write F? F is F cos theta I plus F sine theta J. And finally, the second force, F2, that is the magnitude 600 multiplied by cos of 45. Anyone remembers cos 45? That is root 2 by 2, right? Yeah. And how do I write the y component? The y component is pointing down, isn't it? So I put a negative in front of it. So that's minus magnitude 600 times sine 45. Sine 45 is also root 2 by 2. All right. So I think here, because I know the resultant is horizontal, I can write a very convenient equation. So I'm going to write, just correct me if I'm wrong. Because this resultant only has horizontal component, I only add the j components and put that equal to 0. What about that? So let me start with the j component of f1. What is the j component of f1? That is 25 multiplied by 5, or multiplied by 12. That is 300. Okay. So if I write this one, f1 is f1y. That is 300j. Correct? So this is this term here. And what about the j component of the second force? The j component of second force, that is f2y, that is equal to minus 300 root 2. Correct? And what about the j component of the force itself? The j component of F, that is F sine theta. Yes? So now I know that my resultant only has x component. It doesn't have y component. So all these three added together should be set equal to 0. So that is 300 minus 300 root 2 plus F sine theta is equal to 0. Okay, so this equation, we cannot solve this because it has unknowns, F and theta. So I need a second equation. The second equation is, yes, I do have the resultant R, the magnitude of R, which is Rx. That is, if I want to expand this equation, that is equal to 750 plus 0j. All right, so let's add all the x components together. So the x components added together, 325 divided by 13, that's 25. 25 times 5, that's 125. So f1x. And fx, that is f cos theta. And what about f2x? f2x is equal to 300 root 2. So if I add all these x components together, that is sigma fy. Therefore, sigma fx, that is 125 plus f cos theta plus 300 root 2. All right? Which is equal to 750, isn't it? Remember, that is 750 here. So now you have two equations, two unknown, and I suggest we keep everything f sine theta in one side. That is 300 multiplied by root 2 minus 1 And the second equation, that is f cos theta, that is equal to 750 take away so that I rewrote the equations, and here let me divide left hand side together. That would cancel f, so you'll get tan theta is equal to 300 root 2 minus 1 divided by whatever outcome is, 750 divided by 200. So 200 reciprocate multiplied by 300 times parentheses. So this is 0.6. And then all you have to do is take a inverse tan. And the angle is 31.56. And if you plug that angle in either of this equation, that give you the magnitude of f, right? So f has to be 236. All right, we go to page 56. 56, yes? What was that? Yes, yes. And Nguyen, these are being recorded. You always can access them from the Collaborate Ultra. If you want to watch these are being recorded. I record everything, but in case if you want. Sorry? Yes, yes. I record all the lectures and tutorials. This is being recorded. But it's always better to come to classes rather than watching this. So watching for the second time, not for the first time. Yeah, my experience, if you miss a class, the chances are you're going to miss the recorded one. It's a pattern of vicious circle. All right, so while we're waiting for Natasha, let's do the attendance. All right, Sehrish is here, Natasha is here, Nguyen here, Chaisal away, Daniel, Abdullah away, Jonathan is here, Ahmad is here, Nigel here, Barnaby here, Flynn is here, and Shah is here, Port is here. And Darcy is here. Okay, so let's go to page 56, 57. And do you want to choose a problem or recommend which one you want to solve? Medium difficulty, huh? 227. All right, so here I think the only point here is the angles are being given with respect to different references. Generally, we have a standard way of giving the angle, but here these are different references. But eventually, the resultant, you want to know how much angle it makes with the positive x. And that is the definition of the vector. With every vector, when you define the direction, the standard definition is positive x should travel to the vector in the counterclockwise, and how much it travel, that is called the magnitude. This is a standard magnitude. So that's the only point of this problem. Otherwise, anything else is you already know. So let's try this quickly. And like I said, it's always a good practice to label the forces. If you don't label them, the chances are you get confused. So I call this F1, I call this F2, and we want to find R is equal to F1 plus F2, right? So that's what we want to do. Starting with F1 with I and J, that is magnitude of that 400. X component multiplied by cos 30 in positive direction multiplied by I. And then the J component is magnitude of the force 400 multiplied by sine 30 J. This is F1. So what about F2? F2, right. So that is the X component is positive. right? So we can feel that F2 is positive, that is 800 positive in front of it, multiply by, this is going to be sine of 45, right? Because in that triangle, you're trying to solve this triangle. And then this is sine 45. But when it comes to the j components, we see that this is pointing down. That becomes minus 800. And that is cos 45 j. All right. So yes, then I only have to find out the net x and y component. So 400 times 30 cos, that is 346 and the second one is plus 800 cos 45. Five, 6, 5, 6, 8. So that is 91178. And y components are 28284. That is minus 28. Okay, we have the net x and y values. So r is simply the root squared of these two. So that one is squared plus 91178 squared, and then take the root, is 954 64. That is the magnitude of the force. And with the angle, right, so this is a positive x, negative y. Which quadrant that would be from the 4 quadrants? In which quadrant you have x positive and y negative? That's the 4th quarter, isn't it? Yeah. because in the first quarter, both of them are positive, second quarter, one. All right, so in the third quarter, all you have to do is, I'm looking into the third quarter, that is sigma fy, this is sigma fx, right? So I simply can find one angle from here. I call this theta prime. So that theta prime is simply what? That is tan inverse of big Y divided by big X. Just a magnitude. Don't worry about the sign. That is 282.83 divided by 911.78, and that you have to get the inverse tan. So this is, sorry, just say it again. So that is the fraction 0.31. The angle for that, the tan inverse, is 17 degrees. But because you want to measure it from the positive X, you have to subtract this from 365 or 360. So theta itself, the standard angle measured from the positive X, that is 360 minus 17.23. Sorry? Because the problem is asking measured clockwise from the positive X, right? So what I found as 17, I solved that little triangle here. So I solved this little triangle here, which was like so. That was net forces in X, net forces in Y, and that was theta prime. But then the problem is asking me measured clockwise from the positive X. So this is the X clockwise. Oh, this is clockwise. If this is clockwise, that would be 17. If that was counterclockwise, that's a standard. This is not the standard definition. A standard is X positive should go counterclockwise to get to the vector. But this is asking about the clockwise. If that's clockwise, 17 is the angle. Theta prime is the answer. So this is for counterclockwise. This is for clockwise. Have you seen Chaisal this semester? Have you seen him? Is he in yet? Because he wasn't in the class yesterday.
He said that he's on the first replacement. That's why.
Okay. Hopefully next class will be in. Yes, I really miss all of you. Yesterday, some of you were absent. Yeah.
I don't know what is it. I got the.
You got a different number?
No, yeah.
Yeah, I might made a mistake. Don't worry about that. So you followed the procedure?
Yeah. And
Yeah.
Let's,
Yeah.
let's calculate 10 mu the
Yeah.
this.
I might be wrong. Maybe just double check it.
To calculate this, what equation should we use?
Okay. So you want to calculate that, you need to draw a shape, and that shape is bring your pen. So these are, one is negative, right?
Yeah.
This is negative. So if this is negative, the resultant, I just do it with a different color or solid line. That is the resultant, right?
Yeah.
So this is the resultant, and this has a negative y. This is sigma fy, and this one is sigma fx, right? Now, in this triangle, you have theta here, and theta is tan inverse of this divided by that. This divided by that.
So I got like a negative numbers after that.
Well, no, no. In that, you don't put negative. Because you just want that angle.
Oh, okay, so
Yeah.
well, I don't need to put
Yeah,
it.
no.
That's
It's just you need to remember that's in the fourth quarter, not in the third. Yep. This is a fourth quarter. Yeah, you have a trigonometric circle. This is a trigonometric circle, and a trigonometric circle is where you have x and y. This is first, that is second, this is third, this is fourth quarter. All right. So here, x and y are positive. Here, x is negative, y is positive. Here, both of them negative. Here, x positive, y negative. And the radius of that circle is 1. The radius of this circle is 1. That's the trigonometric circle. The radius is 1. All right. Questions? Are we good? Can we move on? 35. All right. So we have plenty of things left. I think I'm going too slow. Yep. Okay. Now we want to go to the 3-dimension. All right. 3-dimension. You will have to use the Cartesian coordinate, and the question is how there is a specific order between x and y, z. So to remember that order, okay, we try to remember the order of x, y, z. So this is right hand. With your right hand, 4 fingers are going from x to y, and your thumb shows the z direction. Okay, so that is a right-handed coordinate system. So we are dealing with the right-handed, and your thumb shows the z coordinate. So here the difference is you have one net x, net y, net z, and then that's two Pythagoras theorem. So therefore, to find the resultant under the square, there are 3 terms added together. And then some of you came late. I repeat that analogy again. So this analogy is to understand why unit vector is so important. How do you use unit vector? So think of the unit vector as a parent. So there is a parent, but this parent is very short. But that doesn't stop the children to be small or even shorter than the parent, right? So think of there's always a resemblance, a similarity between the parent and children, right? So that similarity is that angle. So the only thing the child would inherit from the parent is that angle. The children could be taller, could be shorter, or even they could be in the opposite direction, male, female, right? So why do we bother to define a new term? Why do we need a new definition? The reason is later on, when we want to describe the forces, we use the position vector. And position vector and the force, they are sharing the same parent. So we do a cheating. Instead of finding the unit vector of the force, we find the unit vector of the position vector, and that is applicable to the force. Okay, so I give you plenty of examples, make sure everyone can remember this. But now, in a nutshell, that's what we are doing. Okay, so unit vector, vector, we always can go from, by having the unit vector, you can describe the vector. Only what you need is just a magnitude, and the unit vector, that's all you need. But that unit vector in 3 dimension is a little bit tricky, because in the 2 dimension, we never mentioned it, but this was there, right? So in the 2 dimension, this is I, this is J, right? So that is, I call this cos alpha, that is the direction cosine for the x. If I want to define a second direction cosine, that would be this angle with this vector. We don't bother to define it, because I know if I have alpha, the second angle, whatever you call it gamma. That already is given, right? Because we know that alpha plus gamma is equal to 90 degrees. We only give one of them. The second one, you can work it out. In the 3 dimension, that's the same story. In the 3 dimension, so that's a general vector, right? So this general vector, if I project it here, it makes one angle with x, I call this alpha, makes another angle with the second one, I call this gamma, and it makes, so it makes an angle with the x, I call this alpha, makes an angle with y, call this gamma, another angle with the z, I call this beta. So do I need to give you all 3 angles? No, 2 of them is enough. In 2 dimension, there are 2 angles. I only give you one. The second one you find. In the 3rd dimension, I give you 2. The 3rd one you find. Here, I can write that cos alpha squared plus cos gamma squared is equal to 1. That is how you find them. Here, I can say cos alpha squared plus cos gamma squared plus cos beta squared is equal to 1. So if you have 2, the 3rd one, you find it from this identity here. That is being set in the 3 dimension. That is the vector, the blue. It has 3 components, I, j, k, but then the magnitude is sum of the squares, and then you take a root. That's the magnitude. But when it comes to the directions are difficult. The angles are 3-dimensional angles. They are not planar angles. So alpha is the vector's angle with x, beta is with y, and gamma is with z. You don't need to have 3 of them. 2 of them is enough. And it's often the case you want to describe the blue one as a force, but force directions is difficult. But the hint is, how do you apply the force? Imagine you are using a chain to apply a force. So with this chain, if I know the position of the beginning, position of the end, that's the position vector. From this position vector, I work out the unit vector, and the very same unit vector applies to the force. So all I need is the magnitude of the force and the unit vector. Unit vector, I get it from the position vector multiplied by this. So let's just do some practice on that. So cos alpha by this triangle, this is x component divided by the hypotenuse, y component divided by the vector magnitude, z component divided by the magnitude. So these are called direction cosine. Direction cosine, there are 3 direction cosines. And yes, that's an identity between them. Cos alpha squared, cos beta squared, cos gamma squared equal to 1. If I give you 2, you find the 3rd one. And then this is very important. When I write the unit vector, so my unit vector would be something like the unit vector would be uxi, uyj, uzk. And you know what? This one is equal to cos alpha. This one is equal to cos beta. This is equal to cos gamma. So if you have unit vector, you have alpha, beta, gamma. If you have alpha, beta, gamma, you can work out the cos alpha, cos beta, cos gamma, and therefore you can work out the unit vector. So depending what is provided to you, you can work this out. Now, when there are two vectors, the resultant is R. What if instead of I give you the vector, I give you two forces which are making it, and then I ask you what is the unit vector? All right, so here, yes, I can add two vectors together, no question about that. But what about the unit vector of that? These products, these multipliers, they are not direction cosines. Why? Because this is not a unit vector. This vector is a child, it's not a parent. So how do you make it child? You have to normalize it. To normalize, you divide children by the magnitude, and that becomes unit. That becomes the unit vector. So I think all these can be better understood by examples. But before I give you example, that is the situation. Here you want to restrict an airplane, and then you are using some cables. But unfortunately, the cables are geometrically complex. And then here, well, we want to describe what forces apply to this point of the wing, what forces applied here. But then the magnitude of the force, I have no problem to measure it. There are some force sensors which give me the magnitude of the force, but there's no such a thing that give you the direction of the force. So what I do is I construct a line from O to this point, and that line I can easily write it as a vector. So remember from calculus, a start point, end point, I can describe this as a vector. I call this a position vector. So position vector, and then from that position vector, I normalize that, making the unit vector, and that normalized unit vector is the same parent as that of the force. I use that unit vector to describe my force. I measured the magnitude of the force, and now I have the unit vector, so I'm fully capable of describing the force itself. Magnitude multiplied by the unit vector. Where do I get the unit vector from? I get it from the position vector. So let's do some exercise. Here, we want to express that force as a Cartesian vector. Well, this is not very difficult because you've been provided the beta, gamma, and alpha is not given. So first thing first, you have to find alpha. How do I find alpha? I start from that identity, rewrite that, and work out alpha. So now I have alpha plus minus. And then by looking into that shape, I can say that my alpha is larger than 90 degrees, right? So therefore, I think the second one is, well, by inspection, alpha is the first answer, not the second answer. All right, so now I have alpha, I have beta, gamma, no problem. So the next step is to construct the unit vector. How do I construct the unit vector? That is cos alpha I, cos beta j, plus cos gamma k. So that is my unit vector. And then the magnitude is given, 200 multiplied by that vector. That's the Cartesian description of the force. Okay, so the full solution is given here. You can access it. I'm just going a little bit fast because we have too many slides left. All right, so here there are two forces acting on a ring, and you want to add the resultant. Anyone can tell me how do I add them? Yes, simply add all the x components together, add all j components, add all k components, including the sign, and that would result into what? The resultant would be this one, 50i minus 40j, 180k. But that is a children, this is not a parent, right? So how do I normalize that? by dividing this into the magnitude of this vector, that becomes the unit vector. So in another word, any vector r is equal to the magnitude of r multiplied by the unit vector, right? So how do I find unit vector? Simply, this is the children, the vector here. I have to divide this by the magnitude of the vector. And what is the magnitude of that one? The magnitude of that one is root of 50 squared plus 40 squared plus 180 squared. Okay, so now I have the unit vector, I have this one, and from the unit vector I can work out alpha, beta, gamma, and also I find the magnitude. So let's do one example here. And here the problem is okay, F2 is not fully specified. F2 only I have the magnitude, right? I don't have its directions. But F1 is fully described. F1, we have both the magnitude and the directions. So how do I do that? Okay, so we have to write this as a vector equation. And I know that the resultant is only having a positive y component, which is equal to 800. So let me write this one for you. Well, I know that this is going to be the resultant. So whatever that is, the resultant is 700i plus cos alpha I plus 700 cos beta j plus 700 cos gamma k. That is F2. And what about F1? F1 is what? F1 is 300 cos 45i plus 300. Well, even more simple than that. So here, F1 is what? F1 is 300 multiplied by cos 45 I plus cos 60 j plus cos 120 k. Okay, so this is what we know, and R is simply equal to 800, was it? 800 in the y-axis. So that is 0i plus 800 positive j plus 0k, correct? And now all I have to do is I add the x component, which is 700 cos alpha plus 300 cos 45, and that I should equal that to 0 because this one is 0. Now the x component, the y component of the resultant, the y component is 700 cos beta plus the j component of this one is 300 cos 60, and that should be equal to 800. Okay, so this one gives me alpha, this one by solution it gives me beta, and finally the z component is 700 cos gamma. Sorry, I again, yes, with I, so that is the country I R. What about it? Because the problem is saying the resultant is only in the positive y and magnitude is 800. So if you want to write it as a vector, it is 0i, 800j, 0k. That's why. So finally, 700 cos beta plus 300 cos 120 is equal to 0, and that one gives me gamma. So now we have alpha, beta, gamma, and we also, yeah, that's what the problem is asking. Okay, so we go to page 65, 66, or too many. So maybe in the remaining time, I do one problem from each slide. Let's go to 65. 65.
So can you go to slide 84?
Sorry,
Can you go to the slide 84?
this is slide. My solution.
When you were making all the measures, why did you take cos for every?
There are two forces added together, F1, F2 added together, and that gives you R. Okay, so I wrote F1 in its component, F2 in its component, but R, that is the resultant. I know it's going to be in the positive y direction. It doesn't have a z or x component.
Because now it's a 3D plane, so how do you determine cos theta or sin theta?
From here, yeah, that's you bring this one to the left hand side, and then cos alpha is the right hand side divided by 700, and then you solve to give you alpha. Is that your question? So you have to solve this equation only has alpha as unknown.
I'm talking about F2 and F1.
Yes. Okay. F1 you have the magnitude, you have the direction cosine. F2 you have the magnitude but not direction cosine.
So why do we take cosine? Because it's in the formula?
That is in the three dimension. The vector is described by direction cosine. Cos alpha, cos beta, cos gamma.
So every time it's cos.
Yeah, yeah. That's a standard. We call this direction cosine. Alpha, beta, gamma. So go back to the slide. The slide would summarize this for you, all right? These are from previous material. All right, now let's go back to the slide and see what we have time for. Okay, I jump into page 66. Okay, so 66, let's try, for example, problem 14, if you like. All right, here I want to express that force as a Cartesian vector, and then um, the magnitude of the force is 500, but then only two angles are given. These are the angles with the z-axis, angle with the x-axis, and the angle with the y is not given. Okay, so here I have gamma is equal to 60, and what is the angle with the x? So what is it? Yeah, so if you go to the slide where we define them, alpha is angle between the vector and x-axis. All right. Okay, with the x-axis, yes, that's 120, right? Alpha is 120, and then how do I find beta? So cos beta squared is equal to 1 minus cos alpha squared minus cos gamma squared. So from here, I can find this is a identity. I have cos alpha squared plus cos beta squared plus cos gamma squared equal to 1. That's the identity. So I simply rewrote it. So that is 1 minus cos 60 squared minus cos 120 squared. So this is equal to half um,
Or 118 minus 16. This is a straight line.
so then I need to take the root of that one. So that's 45 degree. So beta becomes 45 degree. And now that I have beta, I can write this one in this way. So force is 500 times cos 120 I plus cos 60 J plus cos 45 K. Sorry, that was alpha, beta, gamma. This is 45, and this is 60. Okay, so that's the Cartesian description. So we have time for one more Let's go to page 68. 68. Okay, which one? What about doing 246? Okay, how many forces are there? 1, 2, and we want to find the resultant. So that is starting with F1. F1 seems to be in ZY plane. It doesn't have any X component, right? F1 is 0I plus 450 times along the y-axis, that is cos of the angle, which is 3/5. And what about the k? The k component is negative, that is minus 450, and that is sine of this little triangle here, which is 4/5. So that is with the F1. How do I do F2? F2, let me see if I have all the direction cosine. The angle with X is given, with Z is given, but with the Y is not given. So F2, for F2 direction cosine, alpha is 45, beta, we have to find it, and gamma is 60. All right, so cos beta squared is equal to 1 minus cos 45 squared minus cos 60 squared. So cos 45 squared, that is, I think, 1/2 is 0.5, and cos 60 is 0.5 squared is, so this is equal to 0.25, and therefore beta is equal to 60 degrees. Now I can fully describe F2. F2 is 450 multiplied by root 2 by 2I, 0.5 J, and plus, that is, which one? F2. Yeah, 525. Yeah, that's correct. Yeah, thank you for that. Okay, so once you work out this one, I can simply add them together. So the resultant would be, let's simplify this. F1 is 270 J minus 360 K And then okay, now all we have to do is just add them together. And finally, that is minus 97.5. So that is the resultant vector. And if you want to sketch it, we know that this has a positive x component, positive j component, but a negative k component. So that looks like something like this. So in the xy plane, that is positive. In the third direction, that is having a small negative component. All right, so in summary, what we did today, we introduced the second method of combining the vectors. Yesterday, the vectors, if there are only two vectors, we can simply use the triangles or parallelogram to add them. But if there are more than two vectors, the best way of combining them is breaking each force into their Cartesian components, and then all x components are added like scalars, y components are added like scalars, z like scalars. And depending what you have, if the components are given, you can work out the resultant and the direction. If the vector and its direction given, you can break that into the components. And then the next important topic was the unit vector. The unit vector in the 3 dimensions, a vector is equal to magnitude multiplied by the unit vector. So you can work out the unit vector by dividing the vector divided by its magnitude, or children by the magnitude. Normalize it. And every unit vector is represented by its direction cosines, alpha, beta, gamma. And also we keep in mind the identity of cos alpha squared, beta squared, gamma squared equal to 1. So you only need to have 2 of them. The third one, you can work it out. All right. Any question? Thank you very much. And I look forward to see you in the next.
Can you explain this one?
This
Why?
one.
Yeah.
Yeah.
Why
Okay.
F1 is 0R?
I think from that, I gather, if I look into this one, this vector is lying in the y and z component. It doesn't have a component in the x. So this is only in the xz plane.
Okay.
That's what I understand from the fear. The fear, this vector only rests in this plane. It won't project out of that
Yeah,
plane.
and I think they already given our beta.
No, that is for the F2. This is F. I'm talking about F1. F1 is flat.
Yeah, but for the F2, this beta is, I think, is already given at 112.
F2 is with the F2 is with the Y is given. Yes, I think that is. Oh, that 120. I think all 3 angles are given.
So we don't.
Yeah,
Actually,
yeah,
we
yeah.
don't need
That's
this.
yeah. We don't need that. This is already given. Yeah, yeah. Even if that was not there, we got the same answer.
So basically, cost 60 and cost 112 is the same.
Um,
120.
yes.
Okay.
Yeah.
And from the previous one, how can you know 60 or 120?
I think we look into this has a positive component in X, Y, Z. That's
Yeah,
by
but
inspection. They call this by inspection.
yeah, can you show me that one again? Because I'm confused by that one.
This one,
No, the one that
the previous one.
yeah, the one that we need inspection or something.
Okay, I think that was in the slide. That was in the slide.
Yeah.
So, you're talking about
That's,
not this one.
this one is
No.
further away.
Yeah, 60 and 120.
How can you know
So
it's 16? Because
this
I think the
holds.
angle is like kind of big, so it's gonna be 120.
Mhm. Yeah, cos 120, that makes a negative component. This is on the this is the first quarter. That would project this not in that side, on the opposite side. But I think by looking at the figure, I find that this vector is in the first quadrant. So first quadrant only takes the acute angle, not the obtuse angle. Yeah.
Yeah.
Yeah. Not 3-dimensional always not easy to visualize.